Welcome to the fourth lecture in the sixth week of our course, Analysis of a Complex Kind. Today we'll introduce the Riemann zeta function and the Riemann hypothesis. The Riemann zeta function was actually first introduced by Leonhard Euler, who used it in the study of prime numbers. He didn't really use it for complex arguments, he used it for real arguments. We'll see really what Euler's work was next class. In particular, Euler used the properties of the zeta function to show that if you take 1 over every prime number and add up all these numbers, so that will be 1/2 because 2 is a prime plus 1/3, because 3 is a prime plus 1/5, because 5 is prime plus 1/7, plus 1/11, and so forth. He used the properties of the zeta function to show that this sum diverges. So it is a little bit similar to the harmonic series, but we're missing quite a few terms. And so one could think that we're missing enough terms for the series to converge, but he showed the series diverges, which in particular shows that there must be infinitely many prime numbers. But it also shows something about the distribution. The gaps don't get too big, the series still diverges. Bernhard Riemann used the zeta function a century after Euler to obtain results on the asymptotic distribution of prime numbers. Bernhard Riemann's work was seminal in making progress on the distribution of prime numbers. And again, we'll talk more about that next class. Today, we'll study the Riemann zeta function, which wasn't always called the Riemann zeta function. When Riemann talked about it in Euler, they didn't call it the Riemann zeta function, they just called it the zeta function. But this function has gained such importance that it is now called the Riemann zeta function. We'll also talk about the Riemann hypothesis, one of the most famous open problems in mathematics. And next lecture, which is also our last lecture, we'll study the relation between the Riemann zeta function and the distribution of prime numbers. So, in order to introduce the Riemann zeta function, recall that the harmonic series, which is the sum of all 1 over n's, diverges. But if you raise this n in the denominator to a power just slightly bigger than 1, then all of a sudden that series converges. I showed you a proof on how one can see that the harmonic series diverges. Let me quickly show you a little trick on how to see that this series with an s that's slightly bigger than 1, or any value of s bigger than 1, in fact, converges. You can compare this series to an integral, and here's how you do that. The sum 1 over n to the s could be broken up into the first term, 1, which is 1 over 1 to the s, plus the sum n from 2 to infinity, 1 over n to the s. For n equals 2, I get 1 over 2 to the s. Here's a graph of the function 1 over x to the s. In particular, 2 is this number right here, and so 1 over 2 to the s is this value right there. The width of this rectangle that I drew right here is 1, and so the area of this first rectangle is 1 over 2 to the s, the first term of the series. The next term is 1 over 3 to the s, but 1 over 3 to the s can be found right here. That's this height, 1 over 3 to the s. And so the area of this next rectangle is 1 over 3 to the s. Similarly, the area of the next rectangle is 1 over 4 to the s, 1 over 5 to the s, 1 over 6 to the s, and so forth. In other words, the value of this sum from 2 to the infinity of 1 over n to the s is equal to the area of all these rectangles that I drew. And all these rectangles are underneath the curve because I drew right-hand sums for this curve, and this is a decreasing function. And so therefore, that sum is bounded above by the actual area under the curve, which is given by the integral from 1 to infinity of 1 over x to the s dx. So the whole sum from 1 to infinity is bounded above by this extra 1, plus the integral from 1 to infinity of 1 over x to the s dx. And this integral we can actually calculate by finding an antiderivative. 1 over x to the s is actually x to the minus s. And if we write the function like that, it's easier to find an antiderivative. An antiderivative is x to the minus s plus 1, and we need to divide by that. because when I differentiate x to the minus s plus 1, I get minus s plus 1 times x to the minus s plus 1 minus 1, which is x to the minus s. If I wanted to rewrite that again, this is 1 over 1 minus s times 1 over x to the s minus 1. And that's what you see right here. So here's the antiderivative, and I need to evaluate that antiderivative at the two bounds 1 and infinity. Well, I can't really plug in infinity. What this really means, I would plug in a really large value, say r, and then later on let r go to infinity. But when I plug in a really, really large value of r for x, I'm looking at this exponent s minus 1 because s is bigger than 1. S minus 1 is still bigger than 0. If I raise a really, really, really large number to something bigger than 0, it's still really, really large and goes to infinity. So this denominator, x to the s minus 1, goes to infinity as x goes to infinity, or as r goes to infinity. In other words, 1 over that denominator goes to 0. So at the upper bound, my antiderivative goes to 0 if I let the upper bound go to infinity. And therefore, in the limit, what's left is only the antiderivative at the lower bound. When I plug in the lower bound, namely 1, I just find 1 over 1 minus s. Because it is the lower bound, I need to subtract that value. So I end up with 1 minus 1 over 1 minus s, and I can make that into a 1 plus 1 over s minus 1 by just flipping the signs, and then find the common denominator, which is s minus 1. In the end, the value of the right-hand side is s over s minus 1, which is a finite number. So this shows that this series, 1 over n to the s, is bounded above by s over s minus 1. The partial sums, therefore, form an increasing sequence. I keep adding more and more and more, but they're bounded. So the partial sums keep getting bigger and bigger, but they are bounded by s over s minus 1. That can be used to show that the partial sums converge. Therefore, the series converges as long as s is bigger than 1. S being bigger than 1 was really important in finding this exponent s minus 1 bigger than 0. In order to consider the Riemann zeta function, we now let s be a complex number instead of just letting it be a real number as on the previous page. So for s being a complex number whose real part is bigger than 1, we define the zeta function as zeta of s equals the sum from n equals 1 to infinity of 1 over n to the s. This is a zeta, a Greek zeta. It's a little funny, but it's traditional to call the complex variable s instead of z. Normally we would want to call that z, but we're calling it s, and it's just a traditional way because Riemann did that. What do we even mean by n to the s if s is a complex number? Let's quickly figure this out. Remember that for real values of s, we know that n to the s is the same as e to the natural log of n to the s, because e and natural log, they just cancel each other out. But natural log of n to the s, by the rules of logarithm, is s times natural log of n. So n to the s is therefore the same as e to the s times natural log of n. And we use that to define for complex s what n to the s equals. We say n to the s equals e to the s log n, where logarithm is the complex logarithm, but because we're talking about n just being a real number, we can actually just use the natural logarithm right here. One can actually more generally define complex powers where n doesn't even have to be an integer or a real number. So if we have the base being a complex number, we would use this definition, e to the s log n. But because n is actually a natural number, we go back to e to the s ln n, and that is the definition of n to the s for complex values of s. So does this series still converge when real part of s is bigger than 1? Now we're plugging in complex values for s. Does the series still converge? Well, n to the s again is e to the s times natural log of n. Let's find out if this series converges absolutely. So if you put absolute values right there. So absolute value of n to the s is the absolute value of e to the s natural log of n. And we know the absolute value of e to the something is e to the real part of the exponent. But the real part of s times natural log of n, since natural log of n is a real number, the real part of s times natural log of n is simply the real part of s times the natural log of n. But now everything is back to being real. And so this expression is the same as n to the real part of s. Therefore, the series of absolute values of 1 over n to the s is the same as the series of 1 over n to the real part of s. Real part of s is some real number bigger than 1. We showed that if you raise n to any real number bigger than 1, the series converges. So since the real part of s is bigger than 1 by assumption, the series on the right converges. Therefore, we have absolute convergence of the original series, and we know that absolute convergence implies regular convergence, and therefore the series 1 over n to the s converges. In fact, one can show that the convergence is uniform, so equally fast, in portions of the plane where the real part is strictly bigger than 1. So here's 1. If you choose an r that is strictly bigger than 1, then the convergence is going to be uniform in the half-plane that starts at real part equals r. One can use that, the fact of uniform convergence and the fact that the function s goes to 1 over n to the s is analytic, to show that the zeta function is actually analytic in the entire half-plane that starts at 1. Riemann's seminal contribution to the theory of the zeta function and the study of prime numbers is the following theorem. The zeta function has an analytic continuation into the entire complex plane with the exception of the number 1. And this continuation satisfies that zeta of s goes to infinity as s goes to 1. So far, the zeta function is only defined for a real part of s greater than 1. So over here we have a definition. Riemann showed that you can extend this definition to everywhere except the point 1. The point 1 forms a so-called pole of the zeta function. As s approaches 1, the zeta function goes off to infinity. The proof is not easy, but a slightly easier construction is to just construct an extension to the entire right half plane. So again, here's a picture. The zeta function as of now is defined for s greater than 1, and we can actually give a construction that shows you can define it for s greater than 0, again except at the point 1. So that construction is slightly easier, and we'll outline it here. Again, a motivation in R first. The sum from n equals 1 to some bound uppercase n of 1 over n to the s, again, can be viewed as follows. The first term is 1 over 1 to the s. 1 over 1 to the s is this height right here, so the first term is the area of this first rectangle. 1 over 2 to the s is the area of the next rectangle, 1 over 3 to the s, 1 over 4 to the s, and so forth. So this entire sum here is the area of all these rectangles up to the rectangle that starts at n and goes to n plus 1. So this one right there. If I, on the other hand, look at the area under the curve, which is given by the integral from 1 to n plus 1, 1 over x to the s, I'm missing out on all these little pieces. I'm missing this piece. I'm missing this piece. I'm missing this piece, and so forth. So I call each of these pieces delta. This is delta 1 of s. That's delta 2 of s, and so forth. So if I add all these extra delta n's of s's in there, then I get an equality right here for all these areas. And delta n of s is just given by the correct difference here. So here again, this formula that we had. The sum from n equals 1 to uppercase n, 1 over n to the s, is equal to the integral of 1 over x to the s dx plus these little pieces that we were missing. Now observe, the sum on the left converges to the zeta function. This integral here converges to 1 over s minus 1, which is just the integral from 1 to infinity of 1 over x to the s dx. And then there's that sum in the end. Now observe that that sum is an analytic function, and it is analytic in all s whose real part of s is greater than 0. We don't need it to be greater than 1. It's enough to be greater than 0 because we're only looking at 1 over n to the s minus the integral from n to n plus 1, 1 over x to the s dx. So one can actually see that that is an analytic function, and one can moreover show that the sum of all these delta n of s, because we're only talking about little pieces of area, converges as n goes to infinity to an analytic function h of s. So this goes to an analytic function h of s, and that is true in real part of s greater than 0. This goes to zeta of s in real part of s greater than 1. 1 over s minus 1, well, that's kind of defined everywhere except at the point 1. So in the limit, we find that zeta of s, which is the limit of the left-hand side, is equal to 1 over s minus 1 plus h of s. This definitely holds for a real part of s greater than 1 because that's where the zeta function is defined. But the function h is actually analytic in real part of s greater than 0. And this guy here is analytic in the whole complex plane minus the point 1. So the right-hand side lives in a much larger region than what the left-hand side is defined. So here again is this equation. Zeta of s is 1 over s minus 1 plus h of s holds for a real part of s greater than 1. But h of s is actually analytic in real part of s greater than 0. This function here is analytic in the whole complex plane minus the point 1. So in particular, in real part of s greater than 0 minus the point 1. We can therefore use the right-hand side to define the zeta function using the right-hand side in all of the right half plane except for the point 1. And that definition agrees with the original definition for real part of s greater than 1 because we have this equality. But now we can define the zeta function in the entire right half plane except at the point 1. As s approaches 1, h of s is well behaved, and the only thing that's not so well behaved is the term 1 over s minus 1, which goes to infinity. Riemann was actually able to extend the zeta function to an analytic function in all of c minus the point 1, not just in the right half plane minus the point 1. Of much interest are the zeros of the zeta function, so those s's in the complex plane for which zeta of s is equal to 0. One can show the following. The only zeros of the zeta function outside of the strip from 0 to 1 are the negative even integers. So here's the strip between 0 and 1. Outside of that strip, the only zeros of the zeta function are at minus 2, minus 4, minus 6, and so forth. So at the negative even integers. Those are often called the trivial zeros because once you know what the analytic continuation of the zeta function is to the whole complex plane, it's not hard to see that these are zeros of the zeta function. So the region to be studied remains the strip real part of s is between 0 and 1. A key result is that the zeta function has no zeros on the line real part of s equals 1. This is a key result in the proof of the prime number theorem. Again, we'll talk about that during the next lecture. From the fact that there are no zeros on the line where the real part is equal to 1, one can use a functional equation for the zeta function to show that there's also no zeros on the real part of s is equal to 0. And therefore, the only region that is unknown is the region between 0 and 1. So in this region, we still don't really know what happens for the zeros of the zeta function. In his seminal paper, in which Riemann proved the analytic continuation of the zeta function to the whole plane minus 1, he initiated important insights into the distribution of prime numbers. Related to the distribution of prime numbers are the zeros of the zeta function. And in his paper, Riemann expressed the belief in the veracity of the following. Today, this conjecture is called the Riemann hypothesis. Riemann conjectured that in this strip, real part of S between 0 and 1, all zeros of the zeta function are on the so-called critical line, real part of S equals 1/2. So he conjectured that there are no zeros over here, no zeros over here, but all zeros are on this line. In addition to, of course, these zeros, -2, -4, and so forth. Much research has been done in attempts to prove this conjecture. Many things have been proved. For example, it has been proved that the zeta function has infinitely many zeros in that critical strip. It is even known how these zeros are asymptotically distributed. At least 1/3 of the zeros in the critical strip lie on that critical line. That is known. Trillions of zeros of the zeta function have been calculated. So far, all of them lie on the critical line. But that's not a proof. It could be that once you get to a few higher powers, all of a sudden you find a zero that's not on the critical line. So none of these are proofs of the Riemann hypothesis, though they strongly point toward its veracity. So numerical evidence and much research point to the validity of the Riemann hypothesis, but it is to this day unproved and remains one of the most famous unsolved problems in mathematics. In fact, the Riemann hypothesis is on the list of 7 Millennium Prize problems declared by the Clay Math Institute in 2000. Only one of those 7 problems has been solved so far, as of summer 2013. That's the so-called Poincaré conjecture, which was solved by Gregory Perelman. The Riemann hypothesis has strong implications on the distribution of prime numbers and on the growth of many other important functions. It would greatly sharpen many results in number theory. Next class, we'll discuss the prime number theorem, the relation of the Riemann hypothesis and the Riemann zeta function to the prime number theorem, and we'll finish up this course.